In this video, we're going to go through a bit of a more involved example of a stoichiometric calculation. So in the previous video, we went through our first example of using stoichiometry to calculate how much of a product is going to be produced given a certain amount of reactant. And I wanted to go through a problem that's a little bit more involved and kind of takes you through all of the steps of stoichiometry that we've learned at this point. So part A, so let's take it one step at a time. So this is a two-part problem. Part A is telling us write a balanced chemical equation for the combustion of isooctane, C8H18 is this molecular formula, to produce water vapor and carbon dioxide, right? So we want to write a balanced equation that outlines this chemical process, this chemical reaction that's been described in part A, right? So what you need to know, we've looked at a few combustion reactions at this point, right? They always involve some sort of hydrocarbon, which is just a compound that's composed of carbon and hydrogen, and it uses O2, right? It reacts with O2 in order to produce water vapor and carbon dioxide. So whenever you hear combustion reaction, you need to know that O2 is going to be involved in that process. So in general, without balancing the equation, we know that isooctane is involved, right? Our C8H18. That's going to react with O2 to give us CO2 plus water vapor, H2O, right? So what we have here is the general process outlined, right? We don't have nothing's balanced, right? We see that the equation is not going to be balanced, so we still have to do that part. But what we've done is include all of the chemical species that we know are going to be involved in this process, right? So now we want to think, how are we going to balance this guy? Well, we see a pretty stark contrast between the number of carbons and hydrogens on the reactant side and the product side. But both of those are actually easily fixable, right? So we have 8 carbons over here, and we only have one species in the products that involves carbon, right? So we can put an 8 in front of here. And actually, let me use a different color for my stoichiometric coefficients. So we can put an 8 here in front of CO2, and that balances out the carbons, right? And we know we have 18 hydrogens on the reactant side, and we only have one compound here that involves hydrogen. So we can put a 9 in front of here, right, in order to balance out the hydrogens, right? So now we have 9 times 2, that's going to give us 18. So the hydrogens are balanced. We have 8 carbons on the product side, 8 carbons on the reactant side. So those are balanced. Now the only thing left is the oxygens, right? And I've always mentioned here that whenever we have one thing left to balance, right, and you have it by itself as an elemental species, so in this case O2 on the reactant side, it becomes really simple. So I'll show you a little trick here. So we have 8 carbons, 9 hydrogens, right? 18 hydrogens, those are balanced. How many oxygens do we have? Well, we have 8 times 2, 16, right? And you add 9 there, that's going to be 25 oxygens that we have on the product side, right? So if you know how many you need and you have this elemental diatomic here, then what you can do is temporarily use a fraction, right? So we know we want 25 here on the reactant side. So we can use 25 over 2, right? Now you're probably like, wait, hold up. What about Dalton's atomic theory, right? All these atoms have to be countable. We have to use whole numbers, right? You're correct. We will get to that. This is only temporary that we're putting 25 over 2, right? So technically, just off the mathematics, this equation is balanced, right? Because you have half of 25 and 2 oxygens. So this is 25 oxygens, 8 carbons, 18 hydrogens. So technically, mathematically, everything is balanced. But you're right, we have to use whole numbers, right? We can't have these fractions. Easy way to do that is to multiply everything by 2. If we multiply everything by 2, then we get the balanced chemical equation, right? So we'll have, let me write these species again on a new line. So we have C8H18 plus O2, CO2 plus H2O. Right? So now if we multiply all of the stoichiometric coefficients by 2, we get the balanced chemical equation. So this guy will be 2C8H18. This guy is now 25, right? You multiply 25 over 2 by 2. That's just going to be 25. This guy is going to be 16. And then this guy is going to be 18. Right? So now we have, this is going to be our balanced chemical equation. Right? Because now we have no fractions. Everything is whole numbers. So now we've balanced this guy. So this is the balanced chemical equation for the combustion of isooctane, right? So we've solved part A, which was to get our balanced chemical equation. Now let's look at part B. It says, assuming that gasoline is made up of 100% isooctane, right? So 100% this compound, with a density of 0.692 grams per milliliter, what mass of carbon dioxide is produced by the combustion of 1.2 times 10 to the 10 gallons of gasoline, which is the approximate annual consumption of gasoline in the United States, right? So basically we're asking how much CO2 is going to be put up in the air as carbon dioxide gas based on the combustion of this volume of gasoline, right? So I'll go ahead and tell you that we'll need a conversion factor, right? So the conversion factor we'll need is from gallons to milliliters, right? So 1 gallon is 3,785.41 milliliters, right? So gallons is a volume, right? So you get something in gallons, that's the volume of a liquid, right? So we can convert that to milliliters using this conversion, right? So now, how would we go from this volume of gas in gallons to the amount of CO2 produced, right? Well, like I said, the first thing you want to do is figure out, how do I get 2 moles from where I'm at, right? You want to answer the question, how many moles of gasoline is this, right? So that way we can use our balanced chemical equation to figure out how much CO2 that's going to produce, and then we can convert to a mass from there, right? So that's basically the roadmap, right? You start with this volume of gas. You want to figure out how much CO2 is going to be produced. You convert this guy to moles, use your chemical equation to convert, and then go from there, right? So let's go through it. So we're starting with 1.2 times 10 to the 10 gallons of gasoline, right? And we want to convert this guy to moles, right? So we want to be able to first convert this volume to a mass, and the density will allow us to do that, right? We're given the density here, so we can use that to convert from a volume to mass. So first we're going to use this conversion factor, right? We know that for every 1 gallon, we have 3,785.41 milliliters, right? Right? And then from there, we can go from a volume to a mass using the density, right? So we know that for every 1 milliliter, we have 0.692 grams of isooctane for every 1 milliliter, right? So using the density, this gives us the mass of our gasoline. So the mass is going to be 3.1 times 10 to the 13 grams of isooctane. Right, so that gives us a mass for our isooctane. Now we want to take that and convert it to moles, right? So you're going to have to use the molar mass of isooctane. This is going to be 12 times 8 plus 1 times 8, right, for the atomic mass of hydrogen and carbon respectively, right? So using the molar mass to convert this guy, right, we have 3.1 times 10 to the 13 grams of isooctane. Yeah, that's going to be 18, my bad, 18. So this is C8H18. So the molar mass of isooctane is going to be 114.23 grams for every 1 mole of isooctane. And so that's going to give you 2.7 times 10 to the 11 moles of isooctane. All right, so now we got the number of moles of isooctane. So now we have everything we need to start using our balanced chemical equation, right? Now the isooctane is on equal dimensional footing with atoms of or molecules of CO2, right? So now we can use our chemical equation in order to ask how much CO2 would be produced from this amount of isooctane. So starting from this amount of isooctane, right? So we'll have 2.7 times 10 to the 11 moles of isooctane. And from there, we want to use our mole to mole ratio, right? So how much CO2 is produced per isooctane, right? So we have a 16 to 2 ratio, right? 8 to 1 or 16 to 2 ratio here between CO2 and isooctane, right? So for every 16 moles of CO2 that is produced, we consume 2 moles of isooctane. Now, you can reduce this fraction if you want to, right? You can turn this to 8 over 1. Mathematically, it's going to be exactly the same. When I'm teaching these problems, I like to use the same stoichiometric coefficients that exist in the chemical equation just to avoid confusion. But obviously, mathematically, it's valid for you to reduce this fraction to 8 over 1 if you want to. You'll get the same answer. So here, this means that we'll produce 2.1 times 10 to the 12 moles of CO2. Okay, so that's how much CO2 is produced. Are we done yet? We are not. So the question asks what mass of carbon dioxide is produced. And please make sure you guys are reading these questions carefully. That is always an indicator. If it asks you what mass, that means this is not good enough, right? Moles are a measure of quantity. They are not a measure of mass. So you have to convert this guy from moles to mass. So from moles to grams. So all we need is the molar mass for CO2. So 2.1, starting with our amount here, 2.1 times 10 to the 12 moles of CO2. Right, and the molar mass for CO2 is going to be 44.01 grams of CO2 for every 1 mole of CO2. And so that's going to give you 9.5 times 10 to the 13 grams of CO2. Now we're done. That's our final answer. That's a mass. Okay, so this problem was much more involved than the one we did previously and could be indicative of some of the problems that you might see throughout the course. It would ask you to not only balance an equation, but to produce the chemical equation yourself, right? This question just gave us a description of the chemical reaction, and we were required to come up with some of the chemical species that would be involved and write out the chemical equation, then balance it, then use that information to be able to identify the mass of a particular product that would be produced, right? So the level of difficulty that you'll see for these stoichiometric calculations almost directly comes from how involved it is to produce the chemical equation, balance it, how much information you need, conversions you need to do, right? And we were even able to use our knowledge of density, bring that back into the fold and kind of include that here with these stoichiometric calculations.